Okay, so this is part 2 of the lecture for Thursday, March 18th. The next topic to discuss is the topic of eigenvalues and eigenvectors. So we start off with the definition of an eigenvalue and eigenvector. We will only consider square matrices A, and the definition, as you're likely familiar with, is that a vector x such that when paired with a, so a times x, that returns the same thing as returning as just multiplying that vector x by the scalar lambda. So we say such a vector x that has this property is an eigenvector, and lambda is the corresponding eigenvalue. Okay, so to find eigenvalues and eigenvectors, you might have done this, but another way you can write this expression is I can say that if I move the lambda x over to the other side, that gives me ax minus lambda x equals 0, right? And then I can pull the vector x out, which gives me a minus lambda. That's supposed to be a lambda, I apologize. Lambda. But that doesn't make any sense because, so what I'm trying to write here is something like this. I've pulled the x out, so it's over here, and I'm left with a minus lambda, but that doesn't make any sense because a is a matrix and lambda is a scalar, and so their dimensions don't agree. And so we can throw an I in there, and then what you often do when you're asked to find eigenvalues and eigenvectors by hand is you work from here, because x is a non-zero vector. You find the zeros of this expression, this matrix that we have here in parentheses. In this class, you're not going to be required to find eigenvalues and eigenvectors by hand. We will allow the R to find eigenvalues and eigenvectors, and there are lots of, nearly any mathematics program is going to have the ability to find eigenvalues and eigenvectors because it's such an important thing to do. So we'll let the computers do that rather tedious work of finding eigenvalues and eigenvectors. Okay. One other thing that is said here is that it says, also note that we can multiply both sides of 2.4.1 by any non-zero scalar and obtain another eigenvector. So if we have a particular eigenvector and I multiply the left side by 2, what that does is it, of course, would double the number of the size of x here. One way to apply that to would be to double the size of x on both sides, and so that's not all that useful. Eigenvector really has no magnitude. We're going to assume that our eigenvectors have length 1, and so that's nice because we can essentially think of eigenvectors as directions, and they're important directions for reasons that hopefully will become a little bit more clear as we go here. So this example, I'm not going to go through it, but you can show that this vector is an eigenvector of this particular matrix. So here's our matrix A, here's our eigenvector x, and what is shown here is that when you do your matrix vector multiplication on the left-hand side, that's equivalent to taking that vector and multiplying it by a scalar 2 rather than the whole matrix A. Now, if we were to pick other vectors in other directions, we wouldn't get this property. Okay, this says that a fundamental result is that any square matrix always has n eigenvalues. Now, it's sort of like the fundamental theorem of algebra that says there are, for any polynomial there are n roots, but those roots aren't necessarily real, and those roots aren't necessarily distinct, and that's also true for eigenvectors and eigenvalues. Okay, so special matrices have special properties of their eigenvalues and eigenvectors, and so that's where the notes go next, is they talk about matrices and which matrices have special properties. So the first one says that if we have a diagonal matrix, then the eigenvalues are the diagonal entries. So that's sort of the easiest case. Of course, we will be dealing with matrices that aren't diagonal much of the time. This second property says that if lambda and x are an eigenvalue-eigenvector pair for the matrix A, then if we change A in one of these two ways, if we add on I plus A, or we take I minus A, what we will get is new eigenvalues with the same eigenvector. So the eigenvector doesn't change, but the eigenvalues do. So 1 plus lambda is now an eigenvalue for this matrix I plus A, and 1 minus lambda is an eigenvalue for the matrix I minus A. You'll notice that what we're doing in, well, say in this case of I plus A, all we're doing is we're changing the diagonal entries of that matrix, right? Okay. A third property, which is going to be very important for us because we're going to be dealing with positive definite matrices, is that the eigenvalues of a positive definite matrix are positive. And then another one, which I want to talk about next, we'll come back to number 4 here, but number 5 is also a very important one for us. It says that if we have a symmetric matrix, then its eigenvalues are going to be real. And furthermore, the eigenvectors of a symmetric matrix are mutually orthogonal. So if we start off with a symmetric matrix, we're going to end up with, if it's n by n, we're going to end up with n real eigenvalues. We don't have to worry about any complex eigenvalues. Furthermore, the eigenvectors are orthogonal to one another, and that's really nice. Now, if we pair a symmetric matrix with a positive definite matrix, and of course, our covariance matrices are going to be both symmetric and positive definite, then we further have that the eigenvalues are going to be positive. So, putting those ideas together, a covariance matrix will have n real eigenvalues that are all positive, and its eigenvectors are going to be orthogonal. And we'll see some pictures of that here shortly. Going back here to number 4, this tells us something about eigenvalues and eigenvectors of product of matrices. So if A and B are both square with the same size, then of course AB and BA make sense because their dimensions make sense. The product of these two matrices, no matter what order we do it in, so if I take the product AB or I take the product BA, we end up with the same eigenvalues, but we end up with different eigenvectors. So that's something to know. The eigenvalues, I'm going to think of those as magnitudes, are going to be the same, but the directions, the eigenvectors, are different. Okay. This is building on number 5, which we talked about before. If we construct a matrix from the eigenvectors of a symmetric matrix A, then that matrix will be orthogonal, and that makes sense because, well, if the vectors are orthogonal to one another, as we said here, if we build a matrix of them, we end up with an orthogonal matrix. Okay, and that notion of doing that leads us to the spectral decomposition. Okay, so we're going to start with a symmetric matrix A, and we are going to construct a matrix C, whose columns are the eigenvectors of A. And again, these vectors are going to be orthogonal to one another. We're going to also construct a diagonal matrix D, whose elements, the diagonal elements, are the corresponding eigenvectors. So, I'm sorry, eigenvalues. So lambda 1 is the eigenvalue for eigenvector C1. And you can show that the matrix that we started with can be decomposed this way, that this matrix C with these columns here times the diagonal matrix D times C transpose will give you A. And so this is a way of decomposing. You can think of maybe factoring the matrix A. This is a really useful decomposition. Likewise, because C is orthogonal, if I hit both sides of this, let me erase over here. If I hit both sides of this expression on the left with C transpose and on the right with C, what I end up with on the left side is C transpose AC. And of course, because these are orthogonal, C transpose times C is the identity matrix, and we end up with the diagonal matrix D. Okay, so this spectral decomposition is going to be very useful for us, in particular when we talk about, say, principal component analysis. Okay, so let me just illustrate this a little bit more than what the notes showed. I, for some reason, used E's rather than C's. I tend to think of eigenvectors being E's, but here, what I have here is I have C. I'm going to show that C transpose AC is equal to D. So this was our second equation. And so C transpose is going to have rows given by the eigenvectors. It's going to have the C is going to have columns given by the eigenvectors, and I've got A here in the middle. So let's go ahead and do this matrix multiplication. So what I'm going to do here is I'm going to do this part first. And so I'm taking a matrix A, which is n by n, times a matrix C, which is n by n, but I'm going to do it sort of piece by piece by piece. Each one of these is an n by 1 vector. And so if you think about if here is A and here is C, if I want the 1, 1 element, I have to go across row A and down column 1. If I want the 2, 1 element, I have to go across row 2 and down column 1 again, right? And so essentially, to get the first column, so what I was talking about here was I talked about getting this element and that element. To get this whole column, what I have to do is I have to go across all the rows of A and continue to go down that same column of C, and what I'll do is I'll fill in this column of what we get. Well, that gives me this A times E1 for the first column here. And then the second column is going to be A times E2, et cetera, et cetera, et cetera. So that's how I jump from here to there. Okay, now what I have to do is I've got this matrix C transpose, and I've got this new square matrix, which I've already multiplied together to get AC, and I've got to go across the row and down the column, right? So the 1, 1 element would be going across row 1 and down column 1, across row 1 and down column 1. And so, I got ahead of myself, sorry. I've written things here, and what I said is true, but let's simplify things first. What is A times E1? Well, A times E1 is lambda 1 times E1, because E1 is the eigenvector for A. It has corresponding eigenvalue lambda 1, and so I can replace the A in this expression with the corresponding eigenvalues. And then we can do our matrix multiplication. Again, what I've got to do is I've got to go across and down, or I've got to go across here and down that one. So that's what I'm talking about down below. I say, let's consider the 1, 1 element that comes out of this here. Well, what we would do is we'd go across this row and down this column, which gives me E1 transpose lambda 1 E1. And I can, because this is a scalar, I can pull that out, and I'm left with just lambda 1, because E1 transpose times E1 is 1, because these vectors are orthogonal. If I consider any cross element, so the 2, 1 element would be, let's go across row 2 and down column 1. Well, that's going to be E2 transpose lambda 1 E1, and I can again pull my lambda 1 out because it is a scalar. And E2 transpose times E1 is going to give me 0. And so you can see that the II elements in general are going to equal lambda I, and the ij elements are going to equal 0 if I is not equal to j. And that's how we get the diagonal matrix D. Okay, so what we've done is we've shown this, but it's equivalent to showing that. So we've seen the spectral decomposition. And then what we can do is we can use our spectral decomposition to find a square root matrix. So previously we were talking about the eigendecomposition of a symmetric matrix. Symmetric was important because the eigenvectors are orthogonal. If we further say that A is now positive definite, the eigenvalues are going to be positive. And so we can create a square root matrix by factoring A, well, essentially, A to the 1/2 can be given by this. We said that A is equal to C D C transpose before. If I just take the square roots of all of our eigenvalues, that gives me C D to the 1/2 C transpose. And we can see that A to the 1/2 times A to the 1/2, which is going to equal C D to the 1/2 C transpose times C D to the 1/2 C transpose. Well, what that's going to do, this C transpose and C, if I drop the parentheses, is it going to give me an I? That gives me C times D to the 1/2 times D to the 1/2 times C transpose. These D to the 1/2s combine to give me D, and then I have C, D, C transpose, which is equal to A. So this is one way of finding a square root matrix, a matrix which, a square root matrix is a matrix which times itself gives you A. And we don't even have to worry about transposes, of course, because these A's are, because A is symmetric, A to the 1/2 is symmetric. There are other ways to think about getting square root matrices, and so you may have heard of a Cholesky decomposition. But this is a particularly useful way of finding a square root matrix, and we will use this as a tool as well. Okay. The way I'd like to wrap up this bit on eigenvalues and eigenvectors is to talk a little bit about meaning. We throw out these definitions and so forth, but it's a little hard to sometimes understand what the meaning of the eigenvalues and eigenvectors are. And so I'm going to try and do that, and this is hopefully this will give you a little bit of intuition. Okay, so let's just let's just kind of ignore this right now. What we're going to do is we're going to consider the eigenvalues and the eigenvectors of a symmetric and eventually positive definite matrix. And this is the easiest case for interpretation, but these ideas can be extended to non-symmetric matrices as well. So what we're trying to do is we're trying to answer the question, what is an eigenvalue, an eigenvector? So let's put that aside for a second, and let's just consider the easiest function you can think of in univariate space. So y equals ax plus b, and imagine I asked you to describe that function. So what can you tell me about it? Well, what you would say is, duh, the slope is a, and duh, the y-intercept is b, and that completely describes the function. And I say, well, I come back and I say, what do you mean by slope? And you say, well, that's the rate of change of y for every unit change in x. And then I say, in what direction? Well, you'd probably reply, what do you mean, what direction? And that's a completely sensible way to reply, because there's really only one direction to talk about. If we're talking about this linear function, which I've drawn here with intercept b and with slope a, you can either move forward or you can move backward. And if you move forward, you increase a units for every 1 unit of increase, and if you move backward, you decrease a units for every unit backward. I'm sort of describing this for a positive, but of course you can picture it if a is negative. So the rate of change is a, and in the forward direction. Okay, so now let's consider a function going from R2 to R2. So now what we plug in is an x, what we get out is a y, and this is a linear function. And so it's described by a matrix A. And let's further assume that A, of course, A is 2 by 2. The reason I'm doing 2 dimensions is because we can kind of picture it. And notice I've set b equal to 0. So you might think a really simple 2 by 2 function, or function from R2 to R2 would look like this, where there is some intercept, and we could talk about that, but let's not. Let's just make things easier. It wouldn't change this discussion at all. Okay, so we have this very basic function, and I say, okay, describe it. It's a linear function. Tell me what the slope is. And you'd say, well, gosh, that's kind of hard. I mean, the slope, what do you mean by slope? And it's tied up in the 4 numbers of a, because, a is this 2 by 2. And so I can tell you what those 4 numbers are, but that isn't all that meaningful for describing this function, for getting an idea of what it does. So what I say here is the slope, or the rate of change, doesn't boil down to one number. Now, if you go into R and run a little demo which says eigenvalues and eigenvectors of a symmetric matrix, what it's going to do is it's going to try to illustrate this idea. And I can't run R here on my iPad as I'm doing this, but what it's going to do is it's going to start with a whole bunch of x's. So we're going to have x, but importantly, these x's are going to be of unit length. And so what I do is I draw a bunch of points in a circle that have length 1. And then what I'm going to do is I'm going to take some symmetric, it turns out to actually be positive definite matrix A, times x, and I'm going to get times all of these x's, and I'm going to get some y's. And what we're going to see is that the y's form an ellipse that looks something like that. And even more cleverly, I've colored these guys so that their colors, maybe I start with blue and go to red and purple and so forth, but these guys are also colored. So you can kind of see how the points map toward one another. If we look at if we look at A, we do its eigen decomposition, and it gives the eigenvalues and eigenvectors. And it's going to turn out that the eigenvectors are in the direction of the ellipse. So if you look particularly at the colors, like if you look in the direction of the ellipse, the color that's down here on the original X is the same as the color up here. And that's because what's happening is, if I take A times X, it's the same as just taking a scalar times X. So we're not changing this guy's direction, because X is essentially corresponding to the same eigenvalue. So if it's orange down here, it's going to be orange up here. Now, if I look off of the major axes, the color here along this ray coming out from the origin they won't align there. Okay, and furthermore, if you look at the magnitudes of Y, the magnitudes of Y are going to be between the two eigen values. They're going to be less than the larger eigenvalue, lambda 1, and they're going to be greater than or equal to the smaller eigenvalue, lambda 2. And what's happening here is essentially lambda 1 is this magnitude here, lambda 2 is this magnitude here. And so what the eigenvalues and eigenvectors are essentially doing is they're talking about this in two dimensions now, but they're talking about this idea of slope or rate of change. If I go in the direction of this eigenvector, the rate of change is given by its eigenvalue. If I go in the direction of this eigenvector, its rate of change is given by that eigenvalue. But if we go in other directions, well, it's kind of a combination of those two, and we can think of any direction as being a linear combination of the two eigenvectors, because the eigenvectors form a basis for our two-dimensional space. Okay, so please do look at that, our demo. And then formalizing this idea, that if you look at pages 81 and 82 of the book, and I know some of you don't have the book, but they're going to talk about this Rayleigh quotient, and in particular, they're going to talk about a symmetric and positive definite matrix, and they're going to show that the quadratic form with matrix A normalized by the vector x. So if x has length 1, the denominator that I just circled is 1, of course. But the quadratic form, suitably normalized by the length of the vector x, is going to be less than or equal to the largest eigenvalue and greater than or equal to the smallest eigenvalue. Okay, so that's sort of a picture of that. And then the last idea is the eigenvalues and eigenvectors of a covariance matrix. And again, there's an R demo for this. But this is kind of the reverse of what we just did. Think of, instead of having this deterministic function of y equals ax, now we have a process which generates realizations of a random variable. And what we would like to do is understand the behavior or characterize the behavior of those realizations. And of course, that's another way of saying we want to know the distribution of that, or we want to summarize the distribution of that. And one way of summarizing the distribution is through its covariance matrix. And our demo is going to show you that if we start with a particular covariance matrix and generate two-dimensional random normals with that covariance matrix, the eigenvalues and eigenvectors of the covariance matrix describe that cloud of points. The cloud of points is going to be oriented in the directions of the eigenvectors, and the magnitudes of the cloud of points essentially are described by the eigenvalues. So please look at that and run that R demo and get a feel for how the eigenvalues and eigenvectors of a covariance matrix describe the behavior of the points. And in particular, I think you'll look at, well, some variances and so forth, of course, given by the covariance matrix. Okay, so there is let me just, okay. So we will stop here. The next thing to talk about is the multivariate normal distribution. We'll talk about that really quickly. We'll also extend that to talk about the chi-square distribution. But I think this is enough for our lecture on Thursday. This video paired with the part 1 video should be enough, and I will pick up on Tuesday really briefly talking about the multivariate normal distribution. Again, thanks for your understanding, your flexibility in handling the 2 strange lectures this week. There is a homework assignment posted. It is due next Friday. If the having the lectures, if the mix-up on the lectures this week are causing you too much stress to get the homework done by Friday, that's fine. You can turn it in the following Monday, but please recognize that there will be another homework assignment coming very soon after because there are weekly homework assignments. Thanks again. I will see you on Tuesday.